I'd like to talk about cell voltage equalizer with AC internal heating capability for automotive lithium-ion batteries. Lithium-ion batteries for electric vehicles need not only an equalizer but also a heater for preheating. Today, I will propose a cell voltage equalizer with heating capability. This equalizer can achieve simplified system and low cost. Experimental AC heating and equalization test demonstrated the heating capability and equalization capability. As a background, lithium-ion batteries (LiVs) for electric vehicles (EVs) consist of multiple modules, each containing multiple cells connected in series to meet the voltage requirements of loads. However, the cell voltages gradually become imbalanced. This imbalance condition may decrease the amount of usable energy. Also, when the LiV module is charged or discharged in imbalanced condition, these cells in the module may cause overcharge or over-discharge. Overcharge and over-discharge may accelerate degradation of cells. So cell voltage equalizers are indispensable to preclude the voltage imbalance issues. Here, I'll explain the necessity of heating up LiVs. You can see the graph about the discharge characteristic of the LiV with the C/3 rate at 4 temperatures. A horizontal axis shows time, and the vertical axis shows the voltage of the LiV. Focusing on the dark blue line of -20 degrees Celsius, you can see the reduced discharging voltage and time due to the increased internal resistance at low temperatures. These LiV characteristics significantly shorten cruising distance of EVs in practical use. For example, the cruising distance of the 2012 Nissan LiV at -10 degrees Celsius is reportedly nearly halved compared with that under the ideal condition. Therefore, proper heating for LiVs is necessary in cold areas. Therefore, various heating methods has been proposed, and the common way is external heating. This figure shows the LiV system using an external heating technique. The LiV is heated by an external heater through a heating medium like air or liquid. This technique has a problem of low heating efficiency due to a heat leak at a heating medium. And also, in the practical use of EVs, since a LiV system is so huge, uniform heating is difficult. It leads to premature deterioration of LiVs. To solve these problems, internal AC heating techniques have attracted significant research attention. This figure shows a simplified impedance model of a LiV. Internal AC heating techniques apply an AC current to the LiV for heating up with joule heat generated by internal resistance. By heating up the LiV from the inside, high heating efficiency and uniform temperature distribution can be achieved. However, using AC heating techniques for the LiV system causes issues. The issues are the increased system complexity and cost. This figure shows the LiV system using internal AC heating techniques. In addition to a cell voltage equalizer, a heating inverter is necessary to generate an AC heating current. This additional inverter increases the system complexity and cost. So today, I'd like to propose a novel equalizer to solve these issues. Here is the proposed equalizer. The proposed equalizer is a combination of a dual active bridge converter, DAB converter, and a switch module. The proposed equalizer utilizes the primary side inverter of the DAB converter as an AC heating inverter for the internal AC heating technique. LiV module is divided into two parts, V-mod H and V-mod L, and its midpoint is connected to the inverter's output. The proposed equalizer realizes both an equalization capability and an internal AC heating capability in single circuit, so achieve the simplified system and low cost. The proposed equalizer operates either in the AC heating mode or equalization mode. In the AC heating mode, only the AC heating inverter is driven. The AC heating inverter generates an AC heating current IH and supplies IH to the midpoint of the leaf module. To avoid the deterioration of leaves, switching frequency Fs is around few kHz. On the other hand, in the equalization mode, the dub converter and the switch module are driven. Similar to ordinary dub converters, F is around several hundred kHz. The proposed equalizer changes the switching pattern and Fs depending on the operation modes. This slide shows the operation of AC heating mode. Here are theoretical waveforms and the configuration in the AC heating mode. Here is the configuration omitting the secondary side of the dub converter and the switch module. The transformer's primary winding voltage VL changes depending on 4 switching states, generating the trapezoidal current IL. The AC heating inverter operates in 4 switching states of states A, D. In state A, VL is the leaf module voltage V mod half, and in state C, VL is minus V mod half, so changing the direction of VL rapidly. Q2 and Q3 are turned on and off simultaneously, so IH is 0 in states A and C. In states B and D, VL is not 0 due to internal resistance of the leaf, so IL gradually decreases. As opposed, state A and C, Q2 and Q3 are not turned on and off simultaneously in states B and D. So IL flow to the midpoint of the leaf module during state B and D, generating IH. The AC heating operation is divided into 2 modes by combining 4 states. In mode 1, IL flow from the inverter's output to the midpoint of the leaf module during state B and D, so the polarity of IH is positive. In mode 2, IL flows in the opposite direction of mode 1. The polarity of IH is negative. The AC heating inverter repeats 2 modes, so the polarity of IH changes every half switching period Ts. So IH is a square wave shape. IH is divided into a module current I mod H and I mod L respectively. This slide shows the operation of the equalization mode. The proposed equalizer eliminates the voltage imbalance by bidirectional power transfer between the leaf module and a cell. The dub converter manipulates a phase shift angel phi between primary side switching legs Q1, Q4 and secondary side switching legs QH, QL for bidirectional power transfer. The control system measures all cell voltages V1, Vn. The system detects the largest voltage deviation cell as a target cell for power transfer. When the target cell is the least charged, the dub converter operates as phi more than 0 to transfer power from the leaf module to the cell. If the target cell is the most charged, the dub converter operates as phi less than 0. The proposed equalizer performs bidirectional power transfer until the voltage imbalance is eliminated. Now, I'd like to show you the results from our experimental verification. We did an AC heating and an equalization test with this prototype for 12-cell cylindrical LIV module. First, I will show the experimental results of the AC heating test. Here are the experimental conditions of AC heating test and measured key waveforms. The 12-cell LIV module was placed in a thermostatic chamber and the initial LIV temperature was -10 degrees Celsius. Despite attenuating IL and I mod H due to the internal resistance of the LIV, IL was the trapezoidal waveform and I mod H was square wave shape. This graph shows the temperature evolution of the LIV. The LIV temperature rose from -10 degrees Celsius to 0 degrees Celsius in 23 minutes. Right-hand pictures show the temperature distribution observed by the thermography. These results demonstrated that the proposed equalizer heats up LIVs by internal AC heating. This slide shows the experimental result for equalization test. This experimental is used 12 LIVs with large imbalance condition in 3.03, 4.09 volt to verify the equalization performance. The left-hand figure shows measured waveforms when transferring power from the LIV module to the cell. The good agreement with the theoretical ones. The right-hand figure shows measured equalization profiles of cell voltage and standard deviation. These vertical axes are cell voltages and standard deviation. The horizontal axis is time, respectively. Cell voltage imbalance is gradually eliminated by the proposed equalizer as time elapsed. A standard deviation at the end of the experimental was as low as 47 mV. These results demonstrated the equalization capability of the proposed equalizer. I'd like to conclude by making the following points. In this presentation, I proposed the equalizer with the AC heating capability. The proposed equalizer uses a part of the equalizer as an inverter, achieving the simplified system and low cost due to the lack of an additional inverter. I showed some experimental results. First, the proposed equalizer heated up LIVs by internal AC heating technique, demonstrating the internal AC heating capability. Second, voltage imbalance was eliminated by bidirectional power transfer in the experimental equalization test, demonstrating the equalization capability. Thank you for your attention.